Welcome back to the second half of Day 2 of Malaysia Tech Month 2021. To kick off this session, I would like to call upon someone who proves that age is literally just a number. At a tender age of just 7, he has achieved what most 10 times his age have not. Let's welcome second grade student Kautilya Katariya, algorithm lover, problem solver and Guinness World Record title holder for the youngest computer programmer UK to deliver his presentation, followed by a Q&A session by Mr. Ganesh Mahendranathan, Head of Innovation, RHB Banking Group, Malaysia. Over to you, Kautilya.
Hi. You already know me, and I am Kautilya, and today I'm going to talk about computational complexity. So I am a 7-year-old computer explorer and problem solver. And here on the screen, you can see me installing Python when I was around 5.5. And I hold the Guinness World Record title for youngest computer programmer at the age of 6. I knew different kinds of algorithms even before I started coding, and I always had a special love for puzzles and solving problems. Due to lockdown, I got bored at home, so I discovered how to slide on the stairs, and I used a piece of cardboard, a mattress, or some pillows. By the way, the pillow thing wasn't successful. I advise you to not use pillows, but the mattress was rocking. Here's a few seconds with just me sliding. 1, 2, 3, go! I still had lots of time, so here's how I utilized it. I used online computing resources from YouTube and courses from Stanford, MIT, and I learned about artificial intelligence from IBM, and in fact, I'm an IBM certified AI professional. But that's not all. I also explored data science areas and learned how to do data analysis and visualization using Python from IBM. But my most important achievement of the year is in the next slide. So about last week, I got my most important academic certificate, and here on the screen is my Year 2 progress report. I did pretty good. I'm now excited to move to Year 3. I also love drawing, mathematics, swimming, origami, cycling, reading, and playing with my friends and younger brother. So let's dive straight into the topic. So what are algorithms? Algorithms are basically a set of instructions, and they can be very simple, like getting an ice lolly. So number 1, open the freezer. Number 2, take out the ice lolly. And number 3, close the freezer. Or they can be very hard, like make the map of the Andromeda Galaxy with one of those early telescopes. I think the universe also has an algorithm to expand. We just don't know it yet, but they are all around us, and we just keep discovering them. Now, since we didn't make the universe, let's forget about that for a bit, but we made computers, machines, AI technology. So let's talk about algorithms used in programs. So now, to understand computational complexity, you first have to understand big O notation. And big O notation is nothing but forget about small and think big. Actually, all of computational complexity is nothing but forget about small and think big. It's simple because it's just the way to represent something. But it's just a way to represent something. But what is that something? Let's look at some examples to understand that. So let's say I am in a library to find my favorite Sherlock puzzles book. Then I could just ask the librarian and he or she will give it to me. That would be order of 1 time complexity because I'm doing only one step, which is asking the librarian. Obviously, the time taken will depend on how fast the librarian is, but that might relate to space complexity, which is how much memory it takes, which we're not going into in details. In another example, let's say there are no librarians, but I still need to find my book. Then I can start searching rack by rack, one by one, until I find it. That would be order of n time complexity because at max when the book is at the end of the library, I'm doing n steps. And in another example, let's say this time the books are arranged in alphabetical order. So here linear search is still applicable, but is there a more efficient approach? Yes, there is. Binary search. But what is binary search? Okay, let me try to explain. Binary search is a divide and conquer algorithm which works on sorted data, similar to mirrored sort. I don't mean mirrored sort works on sorted data, I mean mirrored sort is a divide and conquer algorithm. So Sherlock Puzzles book starts with an S, the middle letter in the alphabet is M, and S comes after M. So we just need to look for racks M to Z. And then keep on splitting into half until you find it. Now we know what big O notation is. I told you it's simple. We also know what algorithm means. The steps the program takes, but the efficiency of solving the problem depends on how much steps you're taking, if you're talking about time complexity, or how much memory it takes, if you're talking about space complexity. But how do you calculate it? Let's understand that with a simple program. So here on the screen, you can see a simple program to calculate sum of numbers till n. This algorithm involves one step to initialize care 0. Then in the for loop, there are 3 operations running n times. Then the last line of the program is another operation. So in total, you have 1 plus 3n plus 1 operations. But when we talk about big numbers like million, billion, trillion, quadrillion, quintillion, how do small numbers make any difference? They don't. We can ignore all the constants, which will make the expression 3n, then remove the multiplicative factors as well, which will make the expression only n. And then you have your time complexity as order of n. I'm going to say the same thing I said a few minutes ago. Time complexity is nothing but forget about small and think big. No bigger presentation should be done without showing this graph, which is showing the time complexity of different algorithms and gives the indication of how much proportional time it may take if the input size grows. So here you can see on the screen, order of log n is almost constant, and it's the most efficient time complexity for big inputs. Order of n is efficient too. Order of n log n, that's fair at least. But then order of n to power of c, I can't say the same for that. And I definitely can't say the same thing for n factorial or a constant to power of n. But that's only true when we're talking about small inputs. I mean big inputs. When the inputs are more small, then what would happen is that order of log n will perform quite badly, but order of n squared will work the same or even better than order of n. In case you're wondering, my mom helped me to draw these graphs. Initially, I came up with this one. Now let's talk about other kinds of asymptotic complexity. So let's look at the library example again, where I searched for my book rack by rack. That was the linear search one. So here there could be n possibilities, but if I narrow them down, I could find in the first rack itself, and that is the best case. I could find in the middle rack somewhere, and that's average case, but I'm not always that lucky. There is a possibility I could find it in the last rack, or do not find that all in the whole library, and that is the worst case, which is, so the best case is big omega, the average case is big theta, and the worst case is big O notation, which we already looked at. So big O notation is the lower bound, is the upper bound, I mean. Big omega notation is the lower bound, and big theta notation is the average bound. Other than this, we also have two little notations, little omega and little O. They are rough estimates of the upper/lower bounds, but they are not used as much as the big ones, though. So I got this data from one of the books about algorithms, and it shows some interesting figures. As you can see, any algorithm with time complexity and factorial becomes useless after an input more than 20. For 2 to the power of n, that's 40, and squared, a million, still much better than the other two, but still bad. But n log n is quite good, and n is really good. But the grand finale, only 0.03 nanoseconds, is log of n. I mean 0.03 for the per billion at least. Some examples of log of n are binary search, Fibonacci search, and exponential search. Some examples of order of n are radix sort, counting sort, bucket sort. Those are nearly, but linear search is exactly, which we already looked at in the library examples. And then n log n, tube sort, merge sort, quick sort, and heap sort, some other divide and conquer algorithms too. Sum for n squared is bubble sort, selection sort, insertion sort, and stewed sort. 2 to the power n, a great example for that would be the worst case, would be the brute force for calculating the nth Fibonacci number. For n factorial, an example for that would be Heap's algorithm, which is used for generating all the possible permutations of n objects. But we even have algorithms which have order of infinity time complexity, and one of these is Bogo sort. The way it works is by comparing first goes through the list. If it finds out that the element on left is less than the one on the right, then I think you're gonna say it swaps them, but it doesn't. It actually finds another random permutation. Not another A. Even though that could have improved its time complexity to 2 to the power n. Okay, anyways. So now let's look at a couple of sorting algorithms. So the first is insertion sort. So it first marks the first element as sorted, then goes through the list. If it finds out that that element is less than the element just before it, then it puts it before it, and then keeps on going that until it's done through all, until it finds out that it isn't smaller and it's bigger than this element. And then it keeps on doing that until the whole array is in the sorted subarray, and then you're done. You just need to print out the sorted subarray. You should use insertion sort when the data is extremely small or nearly sorted. It's better than bubble sort for that actually. And it also works well where the data sets are almost sorted, because it takes only one iteration of the list in its best case, because it's only omega of n. You shouldn't use it if the list is unsorted to a large extent and the data set is big, and it does not perform well when the list is in reverse order. Its time complexity is order of n squared, and its space complexity is order of 1. And now merge sort. So it keeps on splitting the data into half until you get one element sublist. Then it merges them together until you have a sorted array. I said merge, not join. Otherwise it would have changed to, I think it would have changed the same unsorted array. So merge, it first looks at the first element of both of the list. So for 5, 10 and 2, 7, 8, 5 and 2, 2 is smaller, so put that in first, and then move on to the next element. 7 and 5, 5 is smaller, so put that in next. 10, 7 is smaller, so put that in next. 8 and 10, 8 is smaller, so put that in next. And then finally, you haven't added the 10, so just add that in the end. You should use merge sort when the data is large, but not too large. So for C++, I think that's about more than 10 to the power 6 in size. But for Python, it can be any size smaller than 10 to the power 10, I think. 9 times 10 power of 10. Or a more accurate model would be, I think it's 2 to the power of 64 or 63. And now Tim sort. So it's basically a combination of insertion sort and merge sort. That's why I put that at the beginning. So first analyzes the list, picks which one's better, insertion sort or merge sort. And then it finds out which one's better, and then it uses that sort to sort the list. You should use Tim sort when the data is already sorted. I mean, it works fast for already sorted because it's only omega of n, and in fact it also is used in Python, and it was implemented by Tim Peters in 2002 for use in the Python programming language. Okay, anyway, so you shouldn't use Tim sort when the size is too big. I already told you the constraints. Anyway, when the size is too big, because using merge sort, its time complexity is order of n log n, and its space complexity is order of n. Now binary search. You should use binary search when the data is sorted, and it doesn't work when the data isn't sorted. Its time complexity is order of log n, and its space complexity is order of 1. Now interpolation search. The only difference of it from binary search is I divide it into unequal parts. So it doesn't keep dividing it into half. It might divide so if the element is more at the end, then it might start from more like the end. If it's more at the start, the search is more at the start. So interpolation search, it works best when the data is sorted and uniformly distributed. Only theta of log n, much smaller than binary search log of n. But you shouldn't use it when the data isn't uniformly distributed or sorted. Okay, its time complexity is order of n, and its space complexity is order of 1. So that was the end of my show. That's enough talking about computational complexity. I have a few counts where I would like to connect with you. And I also have a YouTube channel called Kautilya Concepts, where I post videos about how to solve different computing problems. You can search it by Kautilya Concepts Python. It doesn't work when you put in Kautilya Concepts only. Thank you for watching. That was the end of my show.
Thank you, Kautilya, for the lovely, insightful presentation. Now, for most of the audience that might not be aware, if you were to Google Kautilya, you will find 2 child prodigies with the exact same first name. You know, there's a Kautilya Pandit, who was formerly the Google boy in India, and the most recent Kautilya Katariya, whom we have here today. And I tried to understand, so where did this name Kautilya actually come from? You know, and after doing some reading, it's actually the name of a very famous teacher, Chanakya, who is also traditionally identified as Kautilya. And this famous teacher basically adopted a young disciple named Chandragupta, who demonstrated a lot of courage and compassion and eventually became the king, and who created a fantastic legacy. And so that's a beautiful story behind it. For those of you not aware, please look it up. But yeah, so today we have a very special guest with us, Kautilya Katariya. He's the world's youngest programmer. So without further ado, Kautilya, can you tell us a little bit about yourself and your family?
So, so you already know me, and I am Kautilya, and my dad is called Ishwari, and my mom is called Trupti, and I also have a little brother called Shiv.
That's nice. And how old is your little brother?
About nearly 3.
All right, so there's 4 of you. And where do you stay? You're living in the UK?
Yeah, more specifically England, more specifically Northampton.
Northampton, lovely, lovely. So I got a question for you. You got to answer truthfully. Who's the most intelligent in your family?
If you're asking based on age, then it's probably my younger brother, because he already knows how to count to 30, and he's learning how to count 30 to 40.
Wow. All right. So relatively, you would say your younger brother, well, very modest, coming from the world's youngest computer programmer. So perhaps you could share with us, so why did you fall in love with, coding?
So I fell in love because it's fun, and I also like solving puzzles and problems, and computing is just like solving puzzles.
That's nice. That's very nice. I'm a big fan of problem solving myself. I play a little bit of chess. I see a lot of similarities with coding. So how did you start, learn? How did you start learning? Where did you, what was the first book you read or the first video you watched?
The first book I read about coding, you mean?
Yeah.
So the first book I read was when my dad gave me this book that I really loved, and I finished in one day. And also it had some basic computer programs inside it, and I wrote some of them in my laptop. And right now I'm on a different laptop, my old laptop in another room. My old laptop, that's where I put the programs on.
Oh, that's lovely. So what kind of programs, what's your favorite program?
My favorite programs I made so far?
Yeah.
So my favorite program could be the tic-tac-toe one. And the tic-tac-toe one is, I think you know what tic-tac-toe is.
I do know what tic-tac-toe is. One of those games where, you can't lose if you know how to play it. That's nice. Okay, so you did a cool program on tic-tac-toe. That's lovely. What about all these beautiful, pictures behind you? I see a little pi symbol there. And is that an infinity symbol? And another unidentifiable symbol at the top. Could you maybe share a little bit about why you picked those pictures? It's very nice.
So the top one is called Aleph Null, and it is the smallest infinity, and it's countable infinity. So, and countable infinity is basically the self numbers 0 to infinity. And then the second one says you are limitless, and then an infinity. I'm sure we all know what infinity is. And then the last one is pi, which is basically the ratio of the circumference of the circle to the diameter of the circle. And that is approximately 3.1592.
Nice. That's fantastic. And from all the symbols, that are out there, why did you pick this 3?
Because they are my favorite symbols. Omega is also my favorite symbol, but Omega is basically nearly equal to Aleph Null. It is also the smallest infinity, but you can also add Omega by 1, but you can't add Aleph Null by 1, I think.
Okay, so Omega didn't quite make the cut. It just missed the top 3.
Yeah.
And what about, the other photos right there. I see a photo of the Shiva.
The other one is so you mean the other one of them? So the other pictures.
Yeah.
So I don't think I'm sure what the top one is. I don't think I'm sure what that one is.
No worries.
But the one on the bottom of it shows some pictures of. So the first picture is me, my mom, and my little brother. The second picture is my little brother holding up a piece of some Lego-like thing. It's like Lego, it's just bigger. And then the last one is, I'm not sure you can see it, but the last one is basically all the seasons, and so like there's a tree and then there's some leaves on them to represent what season it is.
That's nice. All right. So clearly you value mathematics, you value coding, and your family. You know, these are your big loves. Now, I have a question for you.
Yeah, and also I'm not done. So also the one right next to the tree is so the one right next to a tree, which is on. So the one on the bottom of that row is basically some art that my mom made, and then the one on top of that is, so the top picture is my little brother just in a black and white image, a black and grey and white, I think.
All right.
And then the one the one on the down is me and my little brother at the beach, and then the bottom one is me.
That's nice. That's very nice. Thanks for sharing, Kautilya. So we've learned a little bit about, you know, your love for coding. But now, what about mathematics? You know, do you have any, you know, favorite equation, perhaps? Can you share a little bit?
Yeah, my favorite equation is called Euler's identity, and Euler's identity is one of the most famous equations, and it is e to the power of pi times I plus 1 is 0.
And why is that favorite?
And that is famous because it uses 3 of the most important mathematical constants, E, I, and pi. So E is Euler's constant, which is about 2.718 something. And then I is basically an imaginary number, and it's the square root of -1. And if you multiply it by some number, then what will happen is that it will turn 90 degrees.
Wow.
And then finally, pi is the ratio of the wait, didn't I already tell you what?
You've covered it. Fantastic. All right. Okay, so these are your favorites. Okay, cool. So we've covered mathematics. Now tell me more about artificial intelligence. I heard, you know, you're very interested in it. You know, so how do you think AI is going to change the world?
So I think lots of computers, lots of companies are generating self-driving cars which use AI, and there's also and another way that AI can change the future is maybe the AI can go into flying cars. There is a flying car at the moment, and it's currently in the test run. So maybe the AI could go into the flying cars. So not only there will be less accidents, there would also be about half the traffic because you can go into the air and the land.
Absolutely. Have you seen Back to the Future, by the way? It's a very famous movie about a cool scientist, and he had a car that could travel across different time zones, to the future, to the past. I'll talk to your dad and make sure you catch that. There's a lot of flying cars in there as well. So as a follow-up question, right? So which area of artificial intelligence actually interests you the most?
I think it's probably natural language processing, which is NLP.
Okay, yeah.
And I think it's leading because Google Assistant and Apple Siri, Amazing Alexa, and so they are all types of they all use natural language processing.
Awesome. And for the audience, please don't confuse this NLP with neuro-linguistic programming. It's completely different. All right, moving on. So I'm personally, into cognitive computing. I think that is something that's a very interesting field of research. What are your views on that?
So, and what do you mean by that?
So cognitive computing is the ability for computers to sort of simulate and complement a human's cognitive abilities of decision making. Which is slightly different aspect compared to artificial intelligence, which is not really intended to mimic human thoughts and processes. They're saying that's going to be the next boundary after artificial intelligence. Is that an area you think you would be interested in?
Yeah.
That's nice.
And also, I think no. Yeah, maybe.
Maybe. All right, no worries. All right, so for those of you that, for the audience, right, they might not know really what is the difference between a normal computer algorithm versus an artificial intelligence algorithm. So how would you try and, help them understand the difference?
So, the difference between them is that AI algorithms take in a lot of answers, and also they take in the actual input and they give out the rules, but normal algorithms take the rules and taken the rules and also the input and then give out, and then they give out the answers. So it's basically switching the axes around.
Nice. That's a very, very simple explanation of a highly complex topic. All right, so now enough about, okay, we've covered mathematics, we've covered coding, and all your loves, right? Now let's talk about Kautilya, yourself. So what do you do in your free time? What do you like to do on the weekends? Maybe share a little bit about your interests outside of your technical pursuits.
I like, in my free time, I like to play with my little brother, of course, and I also like to watch TV when it's almost nighttime, and if you count that as my free time, and also I love to swim in my free time.
That's nice. You like the beach? You like to swim at the beach as well?
Yeah.
That's nice. That's very nice. So what is your favorite, what do you like watching on TV?
What?
Do you have any favorite show, or have you seen Rick and Morty?
No.
Okay, I'm not sure that's actually a fun show about a mad scientist who goes on amazing adventures with his grandson. So it's one of my favorite shows. That's nice. So another question is more on, your influences, right? So you have, your wonderful parents, but who else would you consider like a role model, someone that you really look up to, and why?
So so probably my mom and my dad, but if you don't include that, then definitely my little brother, because number one, I love him, and number two, he's the only one left in the family. If it's not my mom and my dad.
And what about, you're such a loving brother? That's so sweet. And what about, outside your family? Anyone else? Any famous scientist maybe, or famous mathematician? Are there anyone that you are sort of inspired by? Not at the moment.
Yeah, not at the moment.
That's fine. That's all right. That's cool. And is there anything else you would like to share with the audience? Things that you might find pretty interesting, or things that, they can learn more about you.
No, I don't think anymore.
That's fine.
To share.
What advice would you give to, young people like yourself, that are looking to learn how to code? Like, what advice would you give children?
I would advise them to keep on practicing, because you know what they say, practice makes perfect. And I would also say to solve puzzles and also have a refreshing break. And I don't mean like video game break, I mean like play outside. So play outside before solving any problem.
Absolutely. So study and life balance, right?
Yeah.
That's nice. If you could go into a time capsule, 20 years in the future, what do you think Kautilya 20 years from now would be? Would you be a scientist, or would you be a mathematician, or
Definitely a scientist or a computer scientist.
okay.
Or both.
Okay. That's awesome.
You can get multiple jobs, can't you?
For sure. Yes, you can. You can. So you can be a computer scientist and a mathematician.
I said scientist, not mathematician.
Okay, just scientist. Okay, that's nice. All right. Thanks so much, Kautilya. We've just reached the end of our session. This is really insightful. I've learned so much from you, from your presentation, and then from yourself. And it's very inspiring, the things that you value, and you're pursuing your passions. And with that, we'll bring the interview, to an end. Any last words before we bring it to a close, Kautilya?
No.
No. All right. Thank you so much.
Thank you, Ganesh. It looks like you truly enjoyed your conversation with Kautilya. And safe to say that we just got schooled by a 7-year-old. To be honest, I was struggling to even keep up right from the start of the lesson of computational complexities. I might have to rewatch that and learn more from Kautilya. And most certainly the future is bright for this young, brilliant mind. And we look forward to seeing many great things from him. I love how focused he is and how he's absolutely sure he wants to be a scientist, or to have 2 jobs even. He was so honest, and I just love that the eagerness in him. I'll be sure to follow his progress on all his social media platforms. We truly hope that you've enjoyed that session. We've got more coming your way. Next up, we're going to discuss on the digital economy, the cornerstone of sustainable development. Keep joining, and we'll see you soon.